When your X-ray passes through your bone, your X-rays will be absorbed completely. But when your X-ray passes through your muscle, it only absorbs a little, and then the remaining will pass through, right? So there is a need to know how much X-ray has been absorbed once it passes through a medium. Okay, before we go to that, there is one concept called attenuation that you need to know. Now, when your X-ray passes through a medium, it will lose its power, it will lose its intensity as the medium absorbs the X-ray. So attenuation can just be described as decrease in intensity when X-ray passes through a medium. Okay, so if say I have a layer of material here of thickness X and having a linear attenuation coefficient of mu, you can just think of linear attenuation coefficient as just simply some sort of constant that tells you how much X-ray will be absorbed. Okay, it's just a constant which we will give you in the question. So say for example, right now you have X-ray passing through a layer of medium of thickness X and with value of mu. I naught here is your incident intensity. Okay, you can think of it as your original intensity. After it has passed through the medium, the intensity will drop because the medium absorbs some of it. So whatever intensity you have left is this intensity I. Okay, if you were to try to visualize how the intensity is dropping as it passes through the layer of medium, you can say that it follows this graph. Okay, the intensity of any X-ray that passes through a medium, its intensity with distance will decrease exponentially like this. Okay, and because it decreases exponentially like this, the equation to represent this will be this. I is equals to I naught exponential negative mu x. Under your nuclear physics chapter, I mentioned before, in general, if you see something decreasing exponentially with time, like this, you could say that x equals to x naught exponential negative lambda t, right? The general equation was that. After that, this one here, you substitute with count rate, number of nuclei, count rate, or activity, right? Correct? So same thing here. When you're talking about intensity of X-ray as it's passing through a medium, you know that the graph looks like this. It's an exponential decay like this. So the equation that represents the intensity can thus be written like this, where intensity at any particular thickness or any particular distance x is actually equals to I naught exponential negative mu x. Okay, so the only thing you basically changed was this. Instead of talking about time, you talk about thickness. Instead of talking about the decay constant, you talk about the linear attenuation coefficient. So in general, when you want to calculate the amount of intensity that has been absorbed, amount of intensity remaining, you need to use this equation. Okay, so that part is fine. All right, so this part is for your X-ray. So we'll just do some of the questions to have a better understanding of all the materials that we covered here. Go to page 14 of your X-ray, of your medical imaging chapter. Have a look at page 14. All right. Page 14 is on June 2016, P42. Okay, question 12. Question 12 is this one. Now they tell you high energy electrons collide with a metal target producing X-ray photons. The variation with wavelength of the intensity of the X-ray beam is shown. Explain why is there a continuous distribution of wavelengths. Okay, so what they mention here is electrons collide with a metal target producing X-ray photons. Variation of wavelength intensity I of the X-ray beams produced is this one. Explain why is there a continuous distribution of wavelengths. This one is related to what I mentioned earlier here. Okay, your electrons, once they hit, they slow down or they decelerate by different amounts. Hence, you have different photon energies. Hence, you have different wavelengths. Okay, so how you want to answer it is something like this. X-ray photons are produced when electrons are decelerated at the metal target. The metal target here is referring to your anode. Okay. As the electrons undergo a range of decelerations, a continuous range of photon energies is produced. Hence, there will be a continuous distribution of wavelengths. All right. So you have to specifically mention X-ray photons. The keyword is photons. You need to mention that photons are produced when the electrons decelerate at the metal target. All right. So this one will give you maybe a minute to copy that. Right. Then if you finish that, you can have a look at page part 2 and part 3 also now, which I will go through later. Right. Okay, now have a look at part 2. They're asking you, why is there a sharp cutoff at short wavelength? Right? The sharp cutoff refers to this portion, and this is your sharp cutoff. As I mentioned to you, you can think of it in two ways. Sharp cutoff can be thought of as, why is it suddenly cutting the x-axis like this instead of doing it like this? Okay, instead of gradual cutoff. Instead of gradual cutoff, why does it suddenly cut off like this? Or another way of thinking just now I mentioned was that, why is it that it will just suddenly stop here? Why isn't there any other wavelength values below this? Why does it just suddenly stop here at this wavelength? So regardless of how you view it, the answers are the same. Okay. The reason why there's a sharp cutoff there is because it's at that point an electron gives all of its energy to produce an X-ray photon when it is stopped in a single collision. Okay, so sharp cutoff is just that. It's worth 2 marks. So when you want to explain it, you say that it is at that point where your electron is stopped in a single collision so that it gives all of this energy to produce an X-ray photons. All right. So this part is this. All right. Okay, then the other part here would be part 3. They ask you, why is there a series of peaks superimposed on a continuous distribution of wavelengths? The peaks that they're talking about here being superimposed on a continuous distribution of wavelength is talking about this one. Why are there peaks that are combined with the continuous distribution of wavelength here, which was this one? This is your continuous distribution of wavelength. Why is there peaks combined there? Why are there peaks superimposed there? So as I mentioned to you, that one is related more towards this part, where I told you that once your electrons that were accelerated hit your metal anode, the initial electrons of the metal anode were knocked off. So there was a vacancy. So the vacancy must be filled. Electrons from the higher level shell will now drop down to fill the vacancy. But as a result of the electrons dropping down, they will emit photons. Those photons are additional photons that add to your existing photons. So in simple terms, you can just explain it as this now. All right. This question didn't require you to explain it in detail. It's just worth 1 mark. So you say something about the excitation of orbital electrons in metal target cause additional X-ray photons to be produced. This one doesn't tell you the full story. It just tells you part of the story. The full story just now I explained. All right. So this part is okay. So this one you're fine. Then I can move on to part B. All right. Now for part B, they say that in the X-ray imaging of body structures, longer wavelength photons are frequently filtered out of the X-ray beam. State how this filtering is achieved. Now, long wavelength photons is actually referring to photons with low energy, right? Because you see, if lambda is large, long wavelength, the energy of your photon is small. The energy of your X-ray photon is small. This one is referring to your soft X-rays, the ones that I mentioned just now earlier to you. Okay, that doesn't do anything other than giving you unnecessary radiation dosage. So how would you achieve the filtering? How would you filter it off? So as I mentioned to you, you need to use an aluminum filter. You can use an aluminum filter, an aluminum sheet, or aluminum foil placed in the path of the X-ray beam from the tube. So that part is talking about this part. Once you produce your X-rays, they consist of hard and soft X-rays. So you don't want the soft X-ray, so you put an aluminum filter here. Okay, so you put an aluminum filter in the path of the X-ray beam from the tube. All right. So that one is for this. All right. Then after that, if you look at the next page, they ask you to suggest a reason for this filtering. Why did you want to filter off the low energy X-ray photons? Why did you want to filter off the soft X-rays? So as I mentioned to you, the long wavelength X-rays actually don't pass through the body. They are absorbed by the body and increase radiation dosage to the patient unnecessarily. Okay, hence that's the reason why you wanted to filter it off in the first place. All right. Okay, so this one is this. While you're copying that, if you're done with that, you can go to page 1 later on. All right. Yeah, okay. For the reason of this filtering, some 4 choices of answer you can not use is this. If you say long wavelength X-rays are of no use, this one won't be correct. Yeah, we know it's of no use, but you have to be a bit more specific. Why do you say that it's of no use? Okay. And then long wavelength X-ray cause poor contrast. In other words, poor image quality. This one can't really be explained. All right, it's very general, so you also cannot use this. All right, so it's better just to say that because they are absorbed completely by the body and increase radiation dosage. That's why you want to filter it, and also because they don't contribute to the image. All right. So this one is fine. Then you go to page 1. Page 1 is talking about this. Okay. Right. Go to page 1. Then you have 15 P41. Now they ask you what state and explain in the X-ray tube how the hardness of an X-ray beam is controlled. So as I mentioned to you, hardness of an X-ray beam refers to the penetration power of the X-ray beam, or in other words, the energy of the X-ray beam. If you want to control the hardness, the power of the X-ray beam, you need to change the tube voltage. Okay, so this one is a 3-mark question where you have to explain it in this way. Changing the tube voltage changes the acceleration potential of the electrons. The electrons striking the anode would have changed speed and hence kinetic energy. Alright, thus the X-ray produced will have different wavelengths and frequency, and therefore different energy. Maybe this one I need to change a little. The electron striking the anode will change speed and hence the energy. The X-ray photons produced will have different wavelength and frequency, therefore different photon energy. Okay. The keywords was this one. You change the voltage. The electron striking anode would have changed speed and hence kinetic energy. Hence the X-ray produced. Okay. Wait, this one I think maybe you have to change this a little. Thus the X-ray photons produced would have different energies, therefore different wavelength and frequency. Alright. If you write this one, I think it will read much better. You change the field voltage, you change the accelerating potential of the electrons. The electrons striking the anode will now have change speed and hence Ke. Thus the X-ray photons produced would have different energies, therefore different wavelength and frequency. Alright. The confusion here is this. How did this even relate to this? Yeah, this one was a point inside. Okay. But this one was what the marking scheme wanted, so it seems a bit out of place. In order to make it consistent, I think it's better if you write this. The X-ray photons produced will now have different energies, therefore you have different wavelength and frequency. Okay, so that part is okay. Now, the other part for part B, they tell you that you have a parallel beam of X-rays with intensity I naught incident on a medium having a linear absorption coefficient mu or linear attenuation coefficient mu. State an equation for the variation of intensity with thickness x of the medium. They are talking to you about a layer of medium with thickness x having a linear attenuation absorption coefficient of mu. So the incident intensity is I naught, and then after that, the one after passing through the medium is intensity I. What is the equation that relates all of them? As I mentioned to you, you can use this. I is equals to I naught exponential negative mu x. Okay. So that part should be fine. Right. So this one is fine. Then I move on to the one at the bottom. Okay. Now they tell you that data for linear absorption coefficient mu for X-ray in blood and muscle are shown. So just why if the X-ray beam is used to image blood vessels in muscle, contrast on the image would be poor. Now you know that contrast is actually the difference in the degree of blackening between the regions of the image, right? In your case here, they tell you the mu for they want to do an image of blood in muscle, but they tell you that they want you to explain why would the image that you get be poor? Why would the contrast of the image be poor? Now, just now, as I mentioned to you, in order to produce your X-ray image, you need to darken your film, okay? To be able to see the different regions, your film, your X-ray film must be darkened by different amounts. Maybe just maybe I better just write this out. Okay, to produce an X-ray image, the film needs to be darkened. Alright, to produce an X-ray image, and the field needs to be darkened by different amounts for the different regions of the structure. Okay, to produce an X-ray image, the field will need to be darkened by different amounts for the different regions of the structure. To darken by different amounts, the intensity of X-ray on film, the intensity of X-ray on film must be different. So they must be absorbed by different amounts. Okay, they must be absorbed by different amounts by the different regions. Okay, to darken by different amounts, the intensity of X-ray or film must be different, so they must be absorbed by different amounts when passing through different mediums in the structure. Okay, this is what I would say lah. The understanding was this lah. If you want to get an X-ray image, your film needs to be darkened by different amounts for the different regions of the structure. Okay, to darken by different amounts, the intensity of the X-ray film in the first place must be different. So this can only be so if they are absorbed by different amounts when passing through different mediums of the structure. Wait, then I have to change this. Let me just change this last sentence a little. To darken by different amounts, the intensity of X-ray of the film must be different. So they must be absorbed by different amounts when passing through different medium in the structure. Okay, this one, they must be absorbed by different amounts when passing through different medium in different regions. In different medium or different regions now. Okay, passing through different medium or region of the structure. Okay, so this is the general understanding there. So if say I have muscle here, and then you have your blood vessels here. Okay, these are your blood vessels. If you want to produce an X-ray image here, you ideally want muscle to absorb different amounts than your blood vessel, so that whatever intensity of X-ray is incident on your X-ray film, they are also different. So your X-ray film will also darken by different amounts. When they darken, so the thing is that you want the region corresponding to muscle to darken differently than blood vessel. Alright, that can only be true if your intensity absorbed by the muscle and blood vessel are different. If both muscle and blood absorb exactly the same intensity, so whatever comes out of the structure and onto your film will be exactly same intensity. So your X-ray film, you will never be able to see the image because they darken by exactly the same amount. So the idea here is that if you want to get an image, you need to have the X-ray film darkening by different amounts. You want it to darken by different amount, that can only be true if you have different X-ray intensity on the different regions of the film. And that one in turn is only possible if your structure is absorbing the X-ray by different amounts in the first place. Okay, so here, how do you know whether the structure, whether the medium has absorbed very different amounts or has absorbed exactly the same amount, you have to refer to this one. Okay, so you say that since the mu for both medium is very similar, there is similar absorption of radiation for that same medium thickness. Therefore, there will be little contrast. Here, blood and muscle will absorb exactly the same amount of radiation, almost similar amount of radiation. So whatever came out behind it onto your X-ray film, your X-ray film will darken exactly by almost similar amounts for muscle and blood. So you cannot see any clear contrast there. Okay, so therefore there is little contrast. That's the understanding here. All right. Right, this is what I will say. Okay, so page 1 is okay. If you're okay with that, you can go to page 5, I think. Yeah, you can go on to page 5. Right. Page 5 is another one. Okay, page 5. Have a look at page 5. Page 5 is November 15P41. Okay, go to page 5. That one is question 10. Alright, so I'll clear this one off. Now explain what is meant by sharpness and by contrast of an X-ray image. So as I mentioned to you, you need to know the definition for sharpness as well as the contrast. Sharpness is just simply the ease with which edges of the structures can be determined. Contrast is just simply the difference in the degree of blackening of structures. Okay, so that one will give you your 2 marks here. Then after that, if you have a look at part B, they mention to you that a parallel X-ray beam of intensity I is incident on a medium of thickness X, as illustrated in the figure, right? Your medium of thickness X, incident intensity I, transmitted intensity IT. This is kind of like the intensity remaining after passing through the medium. Okay, they tell you the linear absorption or attenuation coefficient mu for 80 kilo EV X-rays in bone and muscle are given here. State with reference to the production of X-rays what is meant by 80 kilo EV X-rays. Now, when you see kilo EV, is this unit of energy or unit of voltage? EV in your nuclear physics, you should have known that EV is actually unit of energy, right? So when you hear this term here, 80 kilo EV, the kilo EV here, you will automatically relate it to energy. Okay, don't relate it to voltage. Okay, so with reference to the production of X-rays, what is meant by 80 kilo EV X-ray? So this one, you know, 80 kilo EV relates to energy of the X-rays, but specifically, is this energy of X-ray the minimum energy, the average energy, or the maximum energy? So the answer here is that when they say to you that your X-rays have this particular energy, it actually refers to you the maximum energy of the X-rays. Okay, as I mentioned to you just now, when your X-rays are produced like this, they come with a range of energies, right? Simply because your electrons were slowed down by different amounts. The one with the highest energy will come from the electron that is stopped completely in a single collision. So this one here that you have is actually referring to the most energetic photon, most energetic X-ray photon produced. Okay, so how do you word it? You would say something like this. I won't really bother with the ones written in pencil here. The ones that is easier to understand is the one in red here. Okay. Now here you will say that for the 80 kilo EV X-rays, the electrons actually have kinetic energy of 80 kilo EV. The X-ray photons would have maximum energy of 80 kilo EV. Now this one here, how you think of it as this? If your electrons have 80 kilo EV energy, it will stop completely. That means max the photon, if you stop completely, all the Ke converted to photon energy. This is the max photon energy. Okay. The electrons have 80 kilo EV energy in the first place. Only for the ones that are stopped completely, all the K is converted to photon energy. This is actually the max photon energy. Now, if not stopped completely, the photon energy produced, the photon energy is less than 80 kilo EV. Okay. So this one is addition to this for you to understand what we mean by this. I just now told you that your X-rays have 80 kilo EV energy, right? This one only refers to the ones where the electrons were stopped completely. This is the max energy. Okay. Electrons at 80 kilo EV, when the electrons are stopped completely, all the K is converted to photon energy. This is the max photon energy. If they're not stopped completely, the photon energy will be less than 80 kilo EV. Okay, so this is what it actually kind of means. Your electrons at 80 kinetic energy of 80 kilo EV, X-ray photons will have maximum energy of 80 kilo EV. All right. So that part is okay. Then after that, you look at part 2. Calculate the ratio of IT over I for 80 kilo EV X-rays passing through thickness of 1.4 centimeter of pole. So what's the ratio of IT over I? Now for the question that you have here, you can modify, you know that the general equation I naught exponential negative mu x applies, right? The only thing you needed to change here was this. Just now when I did this for you, this one was I naught, this one was I, right? Then after that, you get this equation here, right, where I naught is your incident intensity, and then your I is the intensity after passing through the medium. You can use that same thing here too for this one, just that the variables you need to change. This I will be, this I here would be IT naught. This I naught would just be I, following the question here. Okay, it's still the same form of the equation, just that the variables they've used is slightly different now. All right, so you use that the same thing. IT equals I naught exponential negative mu x. Then, oh yeah, here I accidentally wrote the I naught here. All right, it's actually supposed to be I. Here IT equals to I exponential negative mu x. Then after that, IT over I would be exponential negative mu x. So this one, don't bother about that, cancel it off. So sum in the value for your mu, sum in the value for your x, and you get this answer. Now, you don't really need to bother in changing the units back to meter because the units actually cancel off. You see, the mu that you have here is per centimeter. The thickness is also in centimeter. They cancel off. This 1 centimeter, negative 1 centimeter here. they will cancel off. So you don't need to change anything. So the ones you get here is ratio 0.015. So that part is okay. Then after that, if you look at part C, they tell you an X-ray image of the upper leg of a student is produced. Part of the X-ray beam passes through a comparatively large thickness of muscle, and then part of it passes through some muscle and leg bone. Suggest whether the image would have good contrast. Now, just now, as I mentioned to you, if you want a good contrast, your X-ray must darken by different amounts. Your X-ray darkening by different amounts must means that you must have different amounts of X-ray incident on the film, and hence you must have different amounts of X-ray absorbed in the first place when passing through the different mediums. So I can say this. For good contrast, mu x must be different. The mu x here represents amount of X-ray absorbed, isn't it? When you look at this general equation, I equals to I naught exponential negative mu x. I over I naught is exponential, is exponential negative mu x, is in turn exponential mu power x. This one, right? Okay. Now, what does the fraction I over I naught represent? Fraction I over I naught represents fraction of intensity remaining, isn't it? This one is your original intensity, this is your final intensity. If you take final intensity over the original intensity, you will get the fraction of intensity remaining. And this one depends on this. Okay. Now, fraction of intensity remaining has direct correlation with fraction of intensity absorbed, right? Okay. If you absorb a lot, you are going to have very little intensity remaining. If you absorb very little, you have a lot of if you absorb very little, you have a lot of intensity remaining. If you absorb a lot, you will have very little intensity remaining. Okay, the relation is inverse now. So here, whatever fraction of intensity remaining or whatever fraction of intensity absorbed is actually affected by your mu x. Okay, so if you want to have very different amounts of intensity absorbed, very different amount of intensity remaining, which is then incident on your X-ray beam, this one must be very different. So hence, you need to write this. For good contrast, mu x must be very different. Then after that, you say that the mu x for leg bone and some muscle will be very different than that of muscle alone. Therefore, a good contrast will be observed. All right. Now, this one fraction of intensity absorbed. This one here, I think I can mention this to you. If you want to find fraction of intensity absorbed, that one will be equal to 1 minus I over I naught. Okay. Fraction of intensity absorbed would be 1 minus I over I naught. If I over I naught is fraction of intensity remaining, you take 1 minus the fraction of intensity remaining, that one will actually be the fraction of intensity absorbed. You will sometimes need to do this in some of the other questions, right? But what you get from this equation, strictly speaking, is just fraction of intensity remaining. Okay, so that part is okay. Then after that, there should be page 19 that we can have a look at. So have a look at page 19. Okay, so we do one last question, page 19. If you just look at page 19, which is this one is June 17 P41. Okay, this is June 17 P41, question 10. Okay, now what is meant by hardness of an X-ray beam? So as mentioned to you, it is the penetration power of the beam. Greater hardness means greater penetration. Okay, so that part is fine. Then after that, they ask you, how does the hardness of the X-ray beam from an X-ray tube is increased? If you want to increase the power of your X-ray beam or hardness of your X-ray beam, what do? You can say you change the tube voltage, or specifically when you're changing the tube voltage, you can say that you increase the tube voltage. When you're increasing the tube voltage, specifically, you're actually increasing the potential difference between anode and cathode, which is this one here, right? I told you that this one is your tube voltage. It is the potential difference between your cathode and your anode. So you can write that. All right. Or you can also say give a greater accelerating potential difference. So that one is that. Right. Then if you move on to part B is talking to you about the same parallel beam of X-ray radiation is incident separately on samples of bone and of muscle. Data for the thickness X of the sample of bone and muscle together with linear attenuation coefficient mu of the radiation of bone and muscle are given in this figure. Find out the ratio of intensity transmitted through the bone and intensity transmitted through the muscle. Okay. So to understand this one here, you can just think of it as this. You have intensity I naught of your X-ray beam. Okay. The question says this. The parallel beam of X-ray is incident separately on samples of bone and muscle. Okay, the same parallel beam is incident separately on two samples, bone and muscle. So here what it means is that this same parallel beam on one part is incident on muscle, and another part is incident on bone. That incident on it separately. So what you expect to see is that this one would also be I naught, this one will also be I naught, because they're incident separately at the same time for two different material. Okay, so muscle would have mu muscle, bone will have mu of B. Okay, they have their own respective thickness, X of muscle, and this one X of bone. So what you want is the ratio of intensity transmitted through bone, the ratio of intensity transmitted through muscle. Basically, they want the intensity remaining after passing through bone and after passing through muscle. So this one here would be your IB. This one will be your IM. This one will be your IB. Okay. You will still use this equation, but apply separately for this, apply separately for this. Okay. So you use this one. If you're talking about the ratios of the remaining intensity or the intensity transmitted through bone and muscle, you just apply this equation for both cases, take one over the other. You will notice that they share certain things. The I naught is the same for both, because they've really told you that that same beam is incident separately on bone and muscle. So this one you can just cancel it off. Then after that, you use the values of X and mu for the two different materials. So as you can see here, this is centimeter, this is centimeter power -1. They will cancel off, so you don't really need to change from centimeter to meter. You will get your answer as 0.57 7. Can you just have a look at page 19 of your medical imaging worksheet? Just have a look at page 19 of your medical imaging worksheet. Okay, right. Page 19 is June 17 P41. All right. So you're talking about June 17 P41. That one would be this one, question 10. All right. Okay, state what is meant by hardness of an X-ray beam. So as mentioned to you that time, if you talk about hardness of an X-ray beam, it tells you how strong the X-ray beam is. Specifically, how strong is its penetration power. So if they ask you what is the hardness of an X-ray beam, you can just say that it's the penetration of the beam. Greater hardness simply means greater penetration of your X-ray through a medium. Okay. You could also say that rather than having greater penetration, it means that the beam is more energetic. It means you have higher frequency, shorter wavelength, or higher photon energy. It can also mean that if you wanted to say so. Okay. And then the other thing here would be, how do you actually change the hardness or penetration power of an X-ray beam for an X-ray tube? So it's mentioned to you that if you wanted to change the penetration power, the hardness, all you just need to do is that you just need to change the tube voltage. You could say change the tube voltage of the X-ray tube, or if you want to be more specific, you can just say increase the potential difference between the cathode and the anode. So in general, I mentioned to you that this is your X-ray tube. This is where you have that little circuit where this is where you have the circuit where electrons are emitted. Then after that, this part here is known as your cathode. This part here is known as your anode, right? The potential difference between this cathode and this anode here is your tube voltage, which affects the potential, which affects the energy of the X-ray photons you will produce. Okay. So you can just say it's increasing the potential difference between the cathode and the anode, right? So I'll also go with that. Okay. So if nothing else, then let me just move down a little. Okay, now for this part of the question, they say that same parallel beam of X-ray radiation is incident separately on samples of bone and muscle. Data for the thickness X of the samples of bone and of muscle together with the linear attenuation coefficients mu of the radiation in the bone and muscle are given in figure 10.1. So as mentioned to you, mu is just something like constant. It tells you how much of your X-rays will actually be absorbed by the medium itself. Okay. So here they ask you to determine the ratio of intensity transmitted to the bone as well as the intensity transmitted through the muscle. Okay, now to recap a little from last week, I told you that if this one was your incident intensity, this is your remaining intensity, right? After passing through a medium of thickness X and linear attenuation coefficient mu, how would you relate this one and this one together? In other words, how will you relate the final intensity and initial intensity? You can make use of this equation I equals to I naught exponential negative mu x. Alright, that was in general the equation you can use here. Now for this case here, when they ask you to determine the ratio of intensity transmitted through the bone and intensity transmitted through the muscle, it's actually just telling you this. If you read the question, they tell you that same parallel beam of X-ray is incident separately on bone and muscle. Okay. Then after that, they tell you these values here and ask you to find out the ratio of transmitted intensity through bone and transmitted intensity through muscle. If represented visually, it just means this. You have, say, bone here, and then you have, say, muscle here. Okay, this one has its own thickness. This one has its own thickness. This one has mu of muscle. This one is mu bone. Then this one will tell you is 1.5 centimeter. While this one will tell you is actually 4.0 centimeter. So the part where they tell you that your same parallel beam of X-ray is incident separately on samples of bone and muscle, it actually means this. If you have a parallel beam of X-rays like this, they are both incident on these two at the same time. Okay, right? This is what this statement actually means. Same parallel beam of X-ray radiation is incident separately on samples of bone and on muscle. It's not to say that bone is behind muscle or muscle is behind bone. They're not stacked together like that. They're considered to be laid out side by side so that they are exposed to the same initial intensity. Okay, so in your case here, this one is I naught, this one will also be I naught. But because they're passing through different mediums, you will expect that the intensity of the X-rays will be absorbed by different amounts, so that whatever intensity you have remaining would actually be different. So here you will get probably the remaining intensity for bone. This you will get the remaining intensity for muscle. If I want to find out the intensity transmitted to the bone, it is this one. The intensity transmitted to the muscle, it is this one. So this one, I know that the equation is IB exponential negative mu B XP. This one will be sorry, not I naught, my mistake. This one will be IB I naught. This one will be IM I naught exponential negative mu M XP, right? They ask you to find the ratio of intensity transmitted through bone and muscle. They're actually asking you the ratio of IB to IM. That's the, yeah, so that's what they're really asking you. Hence your workings would now look like this. You're basically considering both separately and making a ratio out of it. Okay, so then you get this, right? Okay, now there's no need for you to change the units or any kind for the mu and x because they're both in centimeter. This one x was in centimeter, mu is per centimeter. They actually will cancel each other off, so there's no need for you to change the units. All right, so you should get your answer eventually as 0.557. Okay, the I naught is the same, so they will cancel off. You don't need to know what's the value of I naught. Okay, so this one should be quite straightforward. No issues here. Right, then this one is just that question. That's all. Then after that, we go to page 7. Can you just have a look at page 7? Go to page 7 of your worksheet. Okay, page 7 of your worksheet is talking about this. Now, this one is November 15 P43. So let me just get that clear off first. November 15 P43. Question 11. Okay. Right. Okay, now an X-ray source is placed on one side of a metal plate, as shown in this figure. The intensity of the X-ray beam is measured at points A and B. State two reasons other than absorption of X-ray photons in the metal for the intensity of point A to be different than the intensity of point B. Okay. Yeah, consider now that you have X-ray beams from this X-ray source. You have a parallel beam of X-rays coming here. And then after that, you expect that that same beam of X-ray would have passed through. So the question here is, why is it that intensity at A is not the same as intensity of B? So the obvious reason would be that, from what you've learned just now, is that when you have X-ray passing through a medium, some of the X-ray is absorbed by the medium. That's why your remaining, that's why the intensity that came out is actually different than the one that came in. That one is correct, but you cannot use that reasoning here because you cannot use that as your answer direct here because they've already mentioned that here. Okay. If your line of thought was that because the medium is already absorbing part of the X-ray, that's why the values will be different behind the plate, rather that will be different behind the plate than in front of it. That one is correct, but the answer is written, but that point is already written here in the question, so you cannot use this as your answer anymore. You have to talk about something else, about why does your intensity vary between point A and B. Okay, so there are some answers here that could account for the fact why your intensity is different at these 2 points. The first answer would be the scattering of your X-ray photons in metal. Okay, so if you're talking about scattering of X-ray photons in metal, as I mentioned to you, you could have a parallel beam of X-rays that come in like this, but as it passes through the medium, your X-ray could have a tendency to scatter or deflect in another direction. So say for example, right now, maybe you have 4 parallel beams of X-rays. Only one went in, only one was passing straight through, but the rest, maybe it went like this, it went like this, or this one, it went like this. So if you compare this intensity at point A here and this intensity at point B here, obviously part of the reason why this one would not be the same as this is because they went elsewhere. Because the X-ray photons or the X-ray beams, some of them actually went elsewhere as a result of scattering of your X-ray photons. Okay, and probably an easy way to look at it is something like this now. If I have a parallel beam of X-rays and then I suddenly say that part of some of them actually went sideways or were deflected some other direction, you won't expect the intensity here to be the same anymore. Okay, so what could cause the intensity to be deflecting in different directions? It is due to the fact that when you pass through your medium, your X-ray beams scattered. That is one way you can say here. The X-ray photons scattered in the metal. Okay. When your X-ray beams are scattered, it's also correct to say that the beams are no longer parallel. Right? Okay. Then another one that you could also see as the reason why the intensity at B will be different than intensity at A is reflection of your X-ray photons from your metal. So it could be a case where this one was your metal, then this one was your X-ray photons. What could have happened probably was that maybe one of it actually passed right through, but then the rest of it got deflected as a result of hitting the X-ray, as a result of hitting the metal. So again, if you take that into account, your intensity at A and intensity at B would not be same. So these are the 2 other possible reasons why your X-ray intensity at B will not be the same as A. Absorption is one factor, correct, but scattering of X-ray beam could be another factor, and another last factor could be the reflection of your X-ray photons from the metal surface. Okay, reflection. Okay, that's the keyword. Now, the diffraction of X-ray beam in metal like this, I would say that this point is actually the same as these two. Okay, this one, and this one are actually talking about one and the same thing. So I wouldn't really use these 3 points as separate points that by themselves. They're actually one and the same thing. Right. So this one here is scattering of X-ray beam. This one here is reflection of X-ray beam. Okay, so that much is okay. Then if nothing else, let's just have a look at the ones at the question at the bottom. Okay, now a specimen of muscle and bone undergoes X-ray examination. Parallel beams of X-rays are incident on the specimen as shown in figure 11.2. They told you that the specimen has a total thickness of 4 cm. A section contains a bone of thickness 1.5 cm. Data for the linear attenuation coefficient mu for the bone and for the muscle in the specimen are given in figure 11.3. Now, calculate the ratio of intensity of X-ray beam incident on the specimen and intensity of the X-ray beam emerging from the specimen. Okay, this question here, you need to be careful a bit. They ask you to find ratio of X-ray beam incident on specimen to intensity of X-ray beam emerging from specimen. Now the ones that just now I wrote for you was this one. If you have a medium of intensity mu, thickness x, and then you have incident intensity I naught and remaining intensity I, this one will be I naught exponential negative mu x. So that this one will be I over I naught exponential negative mu x. So this one here you would have identified it as the incident intensity. This one you would have identified it as the emerging intensity, right? This would be given by this. But if you look at this one here, when they say incident intensity to emerging intensity, this one is actually not asking I to I naught. This one is actually asking the inverse of this. It's actually asking I naught over I instead. So they are not the same thing. This one is actually the inverse of what you get. So you cannot just simply just use this equation straight. Alright, so what you should do is probably just to come to the conclusion that if I is I naught exponential negative mu x, I naught over I is just 1 over exponential negative mu x, essentially exponential mu x itself. Okay, so this one here is just to prove this now. I think this one is more straightforward for you to see. Okay, this one I think you probably don't want to use this. You probably should just use this instead here. Okay, so the ratio you just sub it in. You just sub in the values and you should be able to get the answer as 2.94. Okay, so that one is fine. Then you move on to the other one. Okay, then after that they tell you, what about if you're talking about the ratio of the intensities through bone and muscle? Okay, now this one here is a bit different from the others because this one has two different mediums combined together. Now, when you have two different mediums combined together, there's one thing that I didn't say last week. What happens if you have 2 or 3 mediums combined together as your X-ray passes through? This one is just a single medium. The example that you have seen is for only single medium, like this one. What if you have multiple mediums? If say you have multiple mediums, like say maybe you have one medium here, a second medium here, and then a third medium here. This one is maybe mu1, mu2, mu3, and this one here is say x1, x2, and then x3. You could have a case where your intensity, initial intensity, will hit this one first, then it passes through medium 1, medium 2, medium 3, and then it emerges from the other end. This one is your I. So in your case, when you have multiple mediums, the ratio, or rather the relation between your emerging intensity and incident intensity will still be the same form as this. The only difference now is that you add the mu x together. What I mean by that is that I is actually equals to I naught exponential negative mu1 x1 plus mu2 x2 plus mu3 x3. Okay, plus mu3 x3. Okay, so it's the same form, just that you need to add the mu x together. All right, then you can just apply this for your bone and muscle now. Okay, your bone and muscle is this one. You see that your bone and muscle actually has kind of like 3 mediums. This one is medium 1, this one is medium 2, this one is medium 3. Okay, so you could say you want to apply this, but again, as the question mentioned to you, you do not want the ratio of I to I naught. You want the ratio of I naught to I. So if you just rearrange this, eventually you get this answer. I naught over I is exponential mu x1 mu1 x1 plus mu2 x2 plus mu3 x3. Okay, the only difference now is that the negative is no longer there. So again, you just add them up together, and then you get your answer as 177. All right, you get that. Then yeah, you just sub in the answer first for that. Okay, let's sub that one in. Then after that, I need to talk to you about what is I naught over. This is incident intensity.
Mr. Chan,
Yeah.
isn't it the way?
Sorry?
Isn't it I naught at the top bottom?
I naught.
Because based on your formula, you divide it, right? You shift it to the other side.
No, I naught over I, right? You want to find I naught over I, right? Isn't it? Are you talking about question 2?
Yes, correct.
Question 2 is talking to you. Calculate the ratio of incident intensity to emerging intensity for 1 and for 2. What?
Oh no, because what meaning because based on what I see on your formula on the right side, right, the bottom right, right, you say I equals to I naught, then exponential to the power of negative something, right?
Yeah, this one.
Then why the I naught when you shift it to the other side it become on top? You get what I mean?
Then I get what you mean. Okay, this one is your maths word. This one is not wrong to say that I over I naught is equals to exponential negative mu1 x1 plus mu2 x2 plus mu3 x3. Nothing wrong with that. But the question, I'm trying to shift this one so that I can match this one. If the question asks me to give me I naught over I, isn't this the same as you saying this one? I naught over I is the same as 1 over e power negative mu1 x1 plus mu2 x2
Yes.
plus
Correct. Yeah.
mu3 x3. So in turn giving me exponential mu1 x1 plus mu2 x2
Okay.
plus
Yeah.
mu3 x3.
Yeah.
It's the same, right?
Understand. Yeah. So
Okay.
yeah.
So the original equation I started off with is still this. I'm just changing it according to what the question wants. If they wanted I over I naught, then this one no issues. It will just be this. But if the question wants I naught over I, then it will just be this. Because the idea was that the I shift down, this one shift here. Then you get this one.
Correct.
Right?
Yeah.
Okay.
Yeah. Sorry, I didn't see the negative there. Yeah.
Yeah. All right. Yeah, that's the thing. That's why I wanted to highlight this. The question is, you need to be careful whether it's I over I naught or I naught over I. Sometimes they will tend to twist the question a little. Right? Okay. So this is incident intensity. This one is emerging intensity. All right. The reason why I want to talk about this is because of the last question. All right. Okay, now using your answers in one, suggest and explain whether an X-ray image of this specimen is likely to have good contrast. Okay, now if you want to have good contrast, as mentioned to you last week, to get good contrast, very different rates. Last week when I did this to you for you, when you want to produce an X-ray image, if you want to get good contrast, it was mentioned that to get good contrast, the film must darken by different amounts. Okay, at the different regions. At different regions. Then after that, I subsequently mentioned to you, the different regions must therefore absorb X-ray by different amounts. Okay, you can only darken your X-ray film by different amounts at the different regions if the X-rays were absorbed by different amounts in the first place at the different regions. Okay, so here you could also say something about that here. Rather than saying that the X-rays are absorbed by different amounts, you can also say that the X-rays are transmitted by different amounts. Another way to reword this could be saying that rather than saying the different regions or must absorb X-ray by different amount, you could also reword it by saying the different regions must transmit X-ray by different amounts. Thinking of it another way, okay? It is transmitting very different amounts. Region A may be transmitting a different amount. Region B might be transmitting a different amount. If both regions are transmitting by same amount, you will have same amount of X-rays in your X-ray film. Your X-ray films will darken by exactly the same amount. So you cannot see good contrast, right? So you could say absorb by different amount or transmit X-rays by different amount. Okay. Now, the reason why I wanted to say this is because it's related to your answer here. Using your answer in one, suggest and explain why your X-ray image of this specimen is likely to have a good contrast. Right? You're trying to do an X-ray like this, when your X-ray beam is coming in here like this. Okay? Your thing that you're trying to do an X-ray for has purely muscle here and part bone here. So what they're interested in knowing is that if you had an X-ray film here, do you have good contrast? Once you go and pass your X-ray film through this medium here, will you have a good contrast? So you have good contrast, this region and this region must absorb X-ray by very different amounts, so that the amount of X-rays that you have here will be very different. Here will be very different from here, then the darkening here and here will be very different. So then you get good contrast. All right. But as I mentioned to you, rather than saying that the different regions must absorb X-ray by different amounts, you can also say that the different regions are transmitting X-ray by different amounts. So you have different absorption rates. Different darkening rates. So good contrast. Now because they say with reference to your answer in one, which is this one. When you're talking about with reference to your answer in 1, your answer is 1 is talking about ratio I naught to I. So when your ratio is I naught to I, this one is actually telling you your transmission. Okay, this one is actually telling you how many times over is initial I think I will do like this. This one is telling you how many times over is incident intensity larger than emerging intensity. Okay, this is your initial intensity, this is your final intensity, this is your measure or transmission that the question is telling you. Okay, it gives you a measure of transmission. So the ratios in 1 and 2, so the ratios that you see in 1 are very different, so there's good contrast. You see this one is 2.94, you see this one is 1.77. This one is actually telling you that the ratio, this one you see the ratio is very different. It will tell you that there's very different transmission or very different absorption. If you're wondering whether could you just say that each ratio gives you a measure of the absorption, you could also say that now if you wanted to, because they mean the same thing. It's just a matter of your point of view. Do you want to view it in terms of amount absorbed or the amount transmitted? If it helps you to understand this matter, you can also say that each ratio is a measure of absorption. If you wanted to, it's a measure of absorption. The ratios are very different, so there is going to be good contrast. You could say that too if you wanted to. All right. Okay, so that is page 7. Then after that, you have page 28. Yeah. So I will look at page 28 if you're okay with this. Okay, 28 should be quite fast. We can do this very quickly. If you have a look at page 28, 28 is this one. This is June 18 P41. So this one I'll just breeze through it very quickly. Okay, now an X-ray beam is used to produce an image of a model of a thumb. A parallel beam of X-ray radiation intensity I naught is incident on the model as illustrated in figure 12.1. Okay, data for attenuation coefficient mu of bone and soft tissue are shown here. Calculate in terms of intensity I naught, or the incident intensity I naught of the X-ray beam, the intensity of the beam passing, the intensity of the beam after passing through the thickness of 2.8 centimeter of soft tissue and bone and soft tissue. Okay, so this one here, this one I think you can just quickly do this. If you're talking about the intensity of the beam after passing through the thickness, this one is actually asking you about I, intensity I. Incident intensity is really I naught. They want the intensity of the beam after passing through. This one is actually referring to I. If you look at this diagram here, this is your I naught. This is the I that they want. And they want the I in terms of I naught. So this one is just a simple matter of putting in your answers, applying the equation I naught exponential negative mu x. So just put that in, you get 0.080 I naught. And another thing I should mention to you here is that be careful about your final answer. If you write this as I equals to 0.8 I naught, this one is 1 SF. Normally, if you do something like this, they will minus 1 mark because your SF is too little. Final answer in your papers, if they did not state how many they want, usually is minimum 2 SF, maximum 3SF. So this one, they didn't tell you, this one by right, you know it's 0.08 if you use a calculator to calculate, but please be mindful that you should not leave it as 1 SF. You should leave it at 2. That's why there's an additional 0 here. Okay. So get that done and you get 0.080. I know. And then after that, if you go to the other one, find out for bone and soft tissue. This one is a case where you're going through three different mediums, right? 1, 2, 3, right? Okay. But this one and this one can be combined together. This one can combine because they're essentially the same medium. That means they're the same mu. That's why here in the working, if you wanted to find out the intensity I here, in terms of the I naught here, you can still use this equation, I naught exponential negative mu1 x1 plus mu2 x2. But the thing here is that I actually added the muscle here and the muscle here together already. You can do that. Just make sure you use the total thickness of that soft tissue. Okay. Then you get the answer at 0.052 I naught. Okay. Then if that is fine, then you should just continue on. State what is meant by the contrast of an X-ray image is just difference in the degree of blackening between structures. You know that already. Then by reference to your answers in A, suggest whether the X-ray image of the model has good contrast. Now, again, they will ask you, your X-ray image, is it having good contrast? You see here, maybe I should write this one off. If you're talking about the intensity that has just emerged from soft tissue alone, it is 0.08 I naught. Okay. But you're talking about the intensity that is emerged from tissue and bone. This is what you get. You are getting 0.052. 0.052 I naught. So these two are actually very different. Then if you put an X-ray film here, this one is 0.08, this one is 0.052. They're actually going to darken by very different amounts. Okay, sorry, this one is not 0.052, this is 0.00, 0.052. Okay, so this one has larger intensity than this one. So this one won't darken as much, but this one will darken a lot. So you're going to have good contrast. So you can just say that because there's very large difference in their intensity, the contrast you get will be good. Okay, so that one should be fine. Then after that, the last one for X-rays related is page 26. If it's a similar question, I think we can just skip that. All right, have a look at page 26. Okay, 26 is actually, okay, some of it is not really in. That one is question 12. Okay, suggest two causes for the lack of sharpness of an X-ray beam. This one I did mention to you last week in the notes or in the written diagram. You're talking about sharpness. Sharpness is the ease with which the edges of the structure can be determined. So some of the things that will cause lack of sharpness is large anode area, large aperture size or the scattering of your X-ray beam. That one I believe was, let me just try and find the diagram, what I meant by that. That one will be under this one. Okay, I'll just share some screen here for you. This one, I'm talking about this one. Last week I shared a screenshot of some writings on the white screen, right? Sharpness is affected by these three items: anode size, aperture size, and scattering of your X-ray beam. If your anode size is small, you get sharp image. If your anode size is big, you do not get sharp image. For aperture size, it's also the same thing. If your aperture size is small, you're going to get a sharp image. If your aperture size is large, you're not going to get a sharp image. And lastly, scattering of X-ray beam. If your X-ray beam is scattered, you're not going to get a sharp image also, right? So that was this point here from last week. So if you just go back to that answer there, that's what they are talking about here. Large anode area will cause lack of sharpness. Large aperture will cause lack of sharpness. Scattering of your X-ray beams will also cause lack of sharpness. Okay. Now, lack of collimation of beams just simply means that the beams are not parallel. Okay. Beams not parallel is actually a consequence of scattering of X-ray beams. So same thing lah. Or also the reason why your X-ray beam is scattered is also because you do not use net grid. So these 3 points are actually the same thing. Alright. So that part is fine. So far so good with that. Okay. Then if you're okay, then I'll just move to the last part. Now the thickness of a sheet of metal is examined using parallel X-ray beams as illustrated in this figure. Part of the beam passes normally through metal of thickness 3.2 mm. Another part of the beam passes normally through a metal of thickness x mm. The linear attenuation coefficient for X-ray beam in the metal is 1.5 cm. Find out the ratio intensity of X-ray transmitted through 3.2 mm of metal and the intensity of X-ray beam transmitted through x mm of metal. Oh, sorry, the ratio is found to be 0.81. Did not asking to find this, they already found it. They ask you to calculate the thickness x instead. Alright. So this one here, you could say that this I naught is I naught. This one will be the remaining intensity for the 3.2. This one will be the remaining intensity for the x. So the ratio of remaining intensity for 3.2 to 3. Sorry, the ratio in remaining intensity for 3.2 mm thickness to the x millimeter thickness is already given as 8.1. The question wants you to find x. So you know that if you're talking about this, the same general equation of I naught exponential negative mu x applies. Alright. So you can just use this to make an expression for the ratios. Before you make an expression for the ratios, you know that I naught for both is constant. So you can cancel it off. I is actually proportional to exponential negative mu x only. So I2 over I1 is exponential mu x2 exponential negative mu x2 over exponential negative mu x1. And after that, you just submit the values. Okay, and solve this. The only thing you need to be careful about is your units. Okay, your mu is in centimeter, but your thickness is in millimeter. So you need to change either one of the units so that they're exactly the same unit type. In my case, because this one is mu is 1.5 centimeter, sorry, yes, 1.5 per centimeter is in centimeter. The thickness for my case, I changed to centimeter. Right? That's why now it's no longer 3.2 instead is 0.32. So then after that you just solve, you get this one. Then you get your answer is 1.8 millimeter. You should really change your answer. Yeah, because this one you are using centimeter, whatever x you get will be in centimeter. Okay, so you get the answer is 1.8 millimeter. Then after that, the last thing here would be the ratios of the intensities is also the ratio of the powers of the X-ray beam. Calculate this ratio in decibels. Okay, calculating ratio in decibel is not covered in this current chapter. It's covered in the last chapter, communication. So what I'll just tell you is that this is just the answer lah. The ratio and intensity is the ratio of powers. You want to find ratios in terms of decibels, it's always 10 log of that ratio. Just take it as this right now. Okay, it will be explored further under your communication chapter.